Electricity is a physical phenomenon resulting from the movement of electric charge. At its core, electricity is the flow of electrons, which are negatively charged subatomic particles found in atoms. Atoms make up all matter, and within each atom, electrons orbit around a nucleus that contains positively charged protons and neutral neutrons. When electrons move from one atom to another in a conductive material, such as a metal wire, an electric current is produced. Electricity exists in different forms, including static electricity and current electricity. Static electricity occurs when there is an imbalance of electric charge in an object, leading to the sudden movement of electrons when contact is made with another object. Current electricity, which is used for power generation and transmission, refers to the continuous flow of electrons through a conductor. This flow is driven by an electric field, which is created by a voltage difference between 2 points. Voltage, measured in volts, represents the electric potential difference that pushes electrons through a circuit. Electricity can be classified into two main types: direct current, DC, and alternating current, AC. Direct current is a type of electric current where electrons flow in a single, constant direction. This type of current is found in batteries and some specialized power systems. Alternating current, which is used in most electrical grids and household outlets, periodically changes direction. AC electricity oscillates back and forth many times per second, a property described by its frequency measured in hertz. The frequency of AC electricity varies by region, with 50 Hz common in Europe and 60 Hz common in North America. Electricity is generated through different methods, including chemical, mechanical, and electromagnetic processes. In a nuclear power plant, electricity is produced through electromagnetic induction. Electromagnetic induction occurs when a changing magnetic field creates an electric current in a conductor. This principle was discovered by Michael Faraday in the 19th century and is the foundation of modern electrical generation. In a nuclear power plant, electricity generation begins with nuclear fission. Footnote: nuclear fission is a fundamental nuclear reaction in which the nucleus of a heavy atom splits into two or more smaller nuclei, releasing a large amount of energy. This process occurs because the nucleus of a heavy atom, such as uranium-235 or plutonium-239, is inherently unstable and can be induced to break apart when it absorbs an extra neutron. The splitting of the nucleus releases not only energy but also additional free neutrons, which can then go on to induce further fission reactions in a chain reaction. At the atomic level, every atom consists of a nucleus made of protons and neutrons, surrounded by electrons that orbit the nucleus. Protons carry a positive charge, and since like charges repel, the nucleus is held together by the strong nuclear force, one of the four fundamental forces of nature. However, in very heavy elements like uranium and plutonium, the strong nuclear force struggles to completely counteract the electrostatic repulsion between the many protons in the nucleus. Footnote: The strong nuclear force, also known as the strong interaction, is one of the four fundamental forces of nature alongside gravity, electromagnetism, and the weak nuclear force. It is the force responsible for binding protons and neutrons together within the atomic nucleus, overcoming the powerful electrostatic repulsion between the positively charged protons. Without the strong nuclear force, atomic nuclei would not exist, and matter as we know it would fall apart into individual protons and neutrons. At the most fundamental level, the strong nuclear force is not directly between protons and neutrons, but instead acts between the even smaller particles that make up these nucleons, quarks. Quarks are elementary particles that come in 6 so-called flavors: up, down, charm, strange, top, and bottom. But protons and neutrons are each composed only of up and down quarks. A proton consists of 2 up quarks and 1 down quark, while a neutron consists of 2 down quarks and 1 up quark. The force that holds quarks together inside protons and neutrons is known as the strong interaction, or quantum chromodynamics, QCD, which is a deeper layer of the strong force. The strong force operates through the exchange of particles called gluons, which act as the force carriers of the interaction. Gluons are analogous to photons in electromagnetism, but unlike photons which do not interact with each other, gluons can interact with other gluons. This self-interaction of gluons is what makes the strong force fundamentally different from other forces. Quarks possess a property known as color charge, which is not related to visible color, but is instead a quantum property that governs their interactions through the strong force. The 3 color charges are conventionally labeled as red, green, and blue. Quarks must always combine in such a way that their color charges cancel out, forming color-neutral particles. This leads to the formation of baryons, such as photons and neutrons, which contain 3 quarks, and mesons, which contain a quark-antiquark pair. The strong force has a unique characteristic called asymptotic freedom, meaning that at extremely short distances, such as within a proton or neutron, quarks behave almost as though they are free. However, as the distance between quarks increases, the strong force becomes stronger rather than weaker, unlike gravity or electromagnetism, which diminish with distance. If an attempt is made to separate quarks, the energy required increases until it is enough to create new quark-antiquark pairs, preventing isolated quarks from ever existing freely. This is why quarks are always confined within hadrons, protons, neutrons, and other particles composed of quarks. Beyond binding quarks together, the strong force also acts at a larger scale to hold protons and neutrons together inside the nucleus. This nuclear force is a residual effect of the deeper strong interaction between quarks. Since protons are positively charged, they experience electrostatic repulsion due to Coulomb's law, which states that like charges repel. The strong nuclear force must therefore be strong enough to counteract this repulsion and hold the nucleus together. Footnote: Coulomb's law describes the force between two electric charges. It states that the magnitude of the electrostatic force between 2-point charges is directly proportional to the product of their charges and inversely proportional to the square of the distance between them. This fundamental law governs the behavior of electric forces and is one of the key principles of classical electromagnetism. The mathematical expression of Coulomb's law is capital F equals small k multiplied by mod of Q1 Q2 divided by R squared, all small, where capital F is the magnitude of the force. Q1 and Q2 are the magnitudes of the two charges, R is the distance between the charges, and K is Coulomb's constant, which has a value of approximately 8.99 multiplied by 10 to the power of 9, capital N dot m squared divided by c squared in a vacuum. Coulomb's law applies to electric charges, which are fundamental properties of matter. Charges can be positive or negative, and like charges repel while opposite charges attract. This means that two positive charges push each other away, as do two negative charges, but a positive and a negative charge will experience a force pulling them together. The force described by Coulomb's law follows an inverse square law, meaning that as the distance between charges increases, the force decreases rapidly. If the distance between two charges is doubled, the force becomes 1/4 as strong. If the distance is tripled, the force decreases to 1/9 of its original strength. This inverse square dependence is a common characteristic of fundamental forces, including gravity. The proportionality constant K in Coulomb's law is related to the permittivity of free space, denoted as epsilon subscript O. 0. It looks more like epsilon naught, you can say. This is a fundamental physical constant that determines how electric fields interact in a vacuum. The relationship between small k and epsilon naught is given by small k equals 1/4 pi epsilon naught, where epsilon naught has a value of approximately 8.85 multiplied by 10 to the power of -12 c squared over n dot m squared. The permittivity of free space represents the ability of the vacuum to allow electric fields to pass through it. In materials other than vacuum, the permittivity changes, affecting the strength of the electrostatic force. Coulomb's law applies strictly to point charges, meaning objects whose charge is concentrated at a single point with no spatial extent. However, real physical objects have finite size and may have charge distributed across their surfaces or volumes. In many cases, if a charged object is spherical and uniformly charged, it behaves as if all its charge were concentrated at a single point at its center when observed from a distance. This is similar to how a planet's mass can be considered to be concentrated at its center when applying Newton's law of gravitation. Electrostatic forces described by Coulomb's law are responsible for a wide range of physical phenomena. They explain why electrons are bound to the nucleus in atoms, why chemical bonds form between atoms, and why materials can be electrically charged. When objects are rubbed together, electrons may transfer from one to another, creating static electricity, which is a direct consequence of Coulomb's law at work. The law is crucial in understanding the behavior of electric fields. An electric field is the influence that a charge exerts on other charges in space, and its strength at any point is determined by Coulomb's law. The direction of the force is along the straight line joining the two charges, meaning that electrostatic forces are central forces. They act along the line connecting the charges and do not depend on their motion. Unlike gravity, which is always attractive, Coulomb's force can both be attractive and repulsive. This difference is what makes electromagnetism much more complex than gravity. In large-scale systems like the solar system, gravitational attraction dominates because all masses attract each other, while electrical forces tend to cancel out because most objects contain equal amounts of positive and negative charge. However, at the atomic and molecular levels, electrostatic forces are far stronger than gravitational forces, which is why they determine the structure of atoms and molecules. One of the most important applications of Coulomb's law is in understanding atomic and molecular interactions. The force between an electron and a proton in a hydrogen atom follows Coulomb's law, and this force determines the structure of the atom. In molecules, the attraction between positive and negative ions in ionic bonds is also governed by Coulombic interactions. Even in covalent bonds, where electrons are shared between atoms, the fundamental forces at play involve Coulombic attractions between nuclei and electrons. Coulomb's law is also the foundation for the electric potential energy of a system of charges. If two like charges are brought closer together, work must be done against the repulsive Coulomb force, increasing their potential energy. If opposite charges are separated, work must be done to overcome the attractive force, again increasing the system's potential energy. This concept is crucial in circuits, capacitors, and electric fields, where energy storage and transfer depend on electrostatic interactions. The principle behind Coulomb's law extends to modern technology in many ways. It is essential for the operation of capacitors, which store energy in electric fields. It explains how electrical forces hold together the charge plates in parallel plate capacitors, and how electrostatic attraction and repulsion affect devices such as touch screens and inkjet printers. It also plays a role in electrostatic precipitators, which remove fine particles from industrial emissions using charged plates. Coulomb's law is experimentally verified with high precision. The first quantitative measurements were conducted by Charles Augustin de Coulomb in the 18th century using a torsion balance, which allowed him to measure the forces between charged spheres. His experiments confirmed that the force varied with the square of the distance, and laid the foundation for later developments in electromagnetism. This law, together with the work of scientists like Gauss, Ampere, and Faraday, eventually led to Maxwell's equations, which describe the full nature of electric and magnetic fields. Coulomb's law is a special case of Gauss's law, which states that the total electric flux out of a closed surface is proportional to the charge enclosed within it. Let me repeat that again. Coulomb's law is a special case of Gauss's law, which states that the total electric flux out of a closed surface is proportional to the charge enclosed within it. In the broader framework of classical electromagnetism, Coulomb's law is a consequence of the inverse square behavior of the electric field produced by a point charge. At very small scales, such as within atomic nuclei, Coulomb's law interacts with the strong nuclear force. The repulsion between protons due to their positive charge would naturally push them apart, but the strong nuclear force overcomes this at very short distances, binding them together. However, in large nuclei, the repulsive Coulomb force can contribute to instability, leading to radioactive decay and nuclear fission. Coulomb's law remains valid in most classical physics applications, but in extreme conditions, such as at very high energies or in quantum electrodynamics (QED), more advanced theories are needed to describe electromagnetic interactions. QED refines Coulomb's law by accounting for the exchange of virtual photons, which mediate the electromagnetic force at the quantum level. Coulomb's law footnote ended. Returning back and repeating the original sentence that led us to the footnote, since protons are positively charged, they experience electrostatic repulsion due to Coulomb's law, which states that like charges repel. The strong nuclear force must therefore be strong enough to counteract this repulsion and hold the nucleus together. The nuclear strong force differs from the fundamental strong interaction in that it does not act directly between quarks, but instead arises due to the exchange of particles called mesons, such as pions. These mesons mediate the interaction between protons and neutrons, creating an attractive force that binds them into a stable nuclei. Unlike the fundamental strong force, which has an effectively infinite range with protons and neutrons, the nuclear strong force is short-ranged, acting only over distances of about 1 to 2 femtometers. 1 femtometer is 10 to the power of minus 15 meters. Beyond this range, the nuclear force rapidly diminishes, allowing atoms to maintain a stable structure. The strong nuclear force explains why atomic nuclei can exist despite the repulsive electromagnetic force trying to push protons apart. In smaller nuclei, such as hydrogen-2, deuterium, or helium-4, the strong force perfectly balances the repulsive forces, keeping the nucleus intact. However, in larger nuclei, such as uranium-238, the balance becomes more delicate. If the repulsive force becomes too great, as in highly unstable isotopes, the nucleus can break apart in a process known as nuclear fission. The interplay between the strong nuclear force and the weak nuclear force governs processes such as radioactive decay, nuclear fission, and nuclear fusion. In nuclear fusion, such as that occurring in the Sun, the strong force binds hydrogen nuclei together to form helium, releasing vast amounts of energy. In nuclear fission, the disruption of the strong nuclear force in heavy nuclei leads to the release of energy which is harnessed in nuclear power plants. The energy released by the strong force is responsible for the enormous binding energy of atomic nuclei. This energy is what Einstein's famous equation E equals mc squared describes in the context of nuclear reactions. When nucleons, protons and neutrons, bind together, some of their mass is converted into binding energy, making the total mass of a nucleus slightly less than the sum of its individual protons and neutrons. This missing mass, known as the mass defect, is released as energy when the nucleus is formed. The strength of the nuclear strong force is evident in the fact that it is roughly 100 times stronger than the electromagnetic force and over 1 trillion times stronger than gravity. However, its short-range nature limits its influence beyond the nucleus. This extreme strength ensures the stability of protons and neutrons, allowing atoms to exist and making the strong force one of the most crucial forces in the universe. Experiments in particle physics, such as those conducted at the Large Hadron Collider (LHC), continue to explore the behavior of the strong force at high energies. The study of quarks, gluons, and their interactions provides insight into the origins of mass, the formation of matter after the Big Bang, and the potential existence of exotic particles that challenge our current understanding of physics. The strong nuclear force is not only essential for the existence of matter, but also plays a role in astrophysical phenomena. It determines the stability of elements within stars, influences supernova explosions, and governs the formation of neutron stars, where matter is compressed to densities so extreme that atomic nuclei merge into a single mass of neutrons held together by the residual strong force. Without the strong nuclear force, protons and neutrons would not exist as bound particles. Atoms would disintegrate, and the universe would be an entirely different place, devoid of the complex structures that make up stars, planets, and life. The strong nuclear force footnote ended, and returning to and repeating the original sentence. Protons carry a positive charge, and since like charges repel, the nucleus is held together by the strong nuclear force, one of the 4 fundamental forces of nature. However, in very heavy elements like uranium and plutonium, the strong nuclear force struggles to completely counteract the electrostatic repulsion between the many protons in the nucleus. This makes these elements relatively unstable and capable of undergoing fission. The most common isotope used in nuclear fission is uranium-235, which makes up only about 0.7% of naturally occurring uranium. In a nuclear reactor or bomb, uranium must be enriched to increase the proportion of uranium-235 to a higher percentage so that a sustained chain reaction can be achieved. Another common fissionable isotope is plutonium-239, which is artificially created in reactors by bombarding uranium-238 with neutrons. When a neutron strikes a uranium-235 nucleus, the nucleus absorbs the neutron and becomes uranium-236, a highly unstable isotope. This instability causes the nucleus to split almost immediately into two smaller nuclei known as fission fragments, along with the release of 2 or 3 additional neutrons. These newly released neutrons can collide with other uranium-235 nuclei, causing them to undergo fission as well. This self-sustaining sequence of reactions is known as a nuclear chain reaction. The fission process releases a massive amount of energy, primarily in the form of kinetic energy of the fission fragments. As these fragments move at high speeds, they collide with the surrounding atoms, transferring their energy and heating up the surrounding material. In a nuclear power plant, this heat is used to convert water into steam, which then drives turbines connected to electrical generators producing electricity. The amount of energy released in nuclear fission is vastly greater than in chemical reactions such as combustion. A single fission event of one uranium-235 nucleus releases about 200 million electron volts (MeV) of energy. By comparison, burning a single molecule of coal or gasoline releases only a few electron volts of energy. This difference explains why nuclear fuels have such an extraordinary energy density compared to fossil fuels. The products of nuclear fission are diverse and include different fission fragments such as barium, krypton, strontium, cesium, iodine, and xenon. These fragments are usually radioactive, meaning they continue to emit radiation as they decay into more stable elements. Some fission products have relatively short half-lives, while others remain radioactive for thousands of years, contributing to the challenge of nuclear waste disposal. In a nuclear power plant, nuclear fission is controlled to ensure a steady and safe release of energy. The key components that regulate the process include fuel rods, control rods, a moderator, and a coolant. The fuel rods contain fissionable material, typically in the form of uranium dioxide pellets stacked inside zirconium tubes. The control rods, made of materials like boron or cadmium, absorb neutrons and can be inserted or withdrawn, to regulate the chain reaction. A moderator, such as water or graphite, slows down fast-moving neutrons to increase the likelihood of fission occurring. The coolant, usually water or liquid sodium, transfers the heat generated in the reactor core to a steam generator or directly to a turbine. If the nuclear chain reaction were left unchecked, the number of fission events would grow exponentially, leading to an uncontrollable increase in energy release. In a nuclear reactor, the balance between neutron production and neutron absorption is carefully maintained to prevent excessive heating and possible meltdown. In contrast, a nuclear weapon is designed to allow an uncontrolled chain reaction, releasing an enormous amount of energy in an instant. The efficiency of a nuclear reactor depends on the ability to sustain a controlled chain reaction without leading to excessive neutron losses. For this reason, reactor designs include neutron reflectors, shielding, and coolant flow systems to optimize performance and safety. The neutron economy of a reactor determines how efficiently neutrons are used to sustain the fission reaction. Some advanced reactor designs, such as breeder reactors, utilize excess neutrons to convert uranium-238 into plutonium-239, effectively generating more nuclear fuel than they consume. One of the major challenges associated with nuclear fission is the management of radioactive waste. The fission process produces long-lived isotopes that require secure storage for thousands of years. Spent nuclear fuel, which still contains fissionable material, is either stored in cooling pools, reprocessed to extract usable isotopes, or placed in deep geological repositories for long-term containment. Fission also produces different types of radiation, including alpha particles, beta particles, and gamma rays. Alpha particles are heavy and can be stopped by a sheet of paper, but they are hazardous if inhaled or ingested. Beta particles are lighter and can penetrate human skin, but are blocked by thick plastic or metal. Gamma rays are high-energy electromagnetic waves that require dense shielding, such as lead or concrete, to prevent exposure. While nuclear fission is an efficient source of energy, it carries risks such as reactor meltdowns, radiation leaks, and nuclear proliferation. Historical incidents such as the Chernobyl and Fukushima disasters highlight the consequences of reactor failures. Though modern reactor designs incorporate passive safety features to minimize the risk of catastrophic failures. Nuclear fission is also utilized in applications beyond power generation. It is used in nuclear propulsion systems for submarines and aircraft carriers, providing long-lasting energy without the need for refueling. It is also used in medical applications, such as producing radioisotopes for cancer treatment and medical imaging. Additionally, nuclear fission is the basis for nuclear weapons, where uncontrolled chain reactions produce explosive yields far greater than conventional explosives. Despite its challenges, nuclear fission remains one of the most concentrated sources of energy available, offering a low-carbon alternative to fossil fuels. It plays a critical role in meeting global energy demands while reducing greenhouse gas emissions. Research is ongoing to improve reactor efficiency, develop safer fuel cycles, and explore alternative nuclear technologies such as thorium reactors and small modular reactors to make fission-based energy more sustainable and secure. In summary, nuclear fission is the splitting of a heavy atomic nucleus into smaller fragments, releasing vast amounts of energy. This energy is harnessed in nuclear power plants through a controlled chain reaction that generates heat, which is then converted into electricity. The process involves complex interactions between neutrons, fuel materials, moderators, and control systems to ensure safety and efficiency. The byproducts of fission include radioactive waste, which must be managed carefully due to its long-term hazards. Nuclear fission has both civilian and military applications, and while it presents risks, it remains a crucial technology for energy production and scientific advancement. Nuclear fission footnote also closed. Returning to and repeating the original sentence. In a nuclear power plant, electricity generation begins with nuclear fission, a reaction in which heavy atomic nuclei such as uranium-235, split into smaller nuclei, releasing energy in the form of heat. This heat is used to produce steam from water, and the steam drives a turbine. A turbine is a large mechanical device with blades that spin when steam passes over them. The turbine is connected to a generator, which is responsible for producing electricity. A generator consists of coils of wire that rotate within a strong magnetic field. When the coils move through the magnetic field, an electric current is induced in the wire, following the principle of electromagnetic induction. The movement of electrons within the generator creates alternating current, which is then transmitted through power lines to supply homes, businesses, and industries. Electricity flows through conductors, which are materials that allow the easy movement of electrons. Metals like copper and aluminum are commonly used as conductors because they have loosely bound electrons that can move freely. Insulators, on the other hand, are materials that resist the flow of electricity. Materials like rubber, glass, and plastic are used as insulators to prevent unwanted electric currents and protect people and equipment from electrical hazards. Electrical circuits are pathways through which electricity flows. A simple electrical circuit consists of a voltage source, such as a battery or generator, a conductor, such as a wire, and a load, such as a light bulb or motor. The voltage source provides the necessary potential difference to push electrons through the circuit. The load converts electrical energy into another form of energy, such as light, heat, or motion. Electricity can be transformed into various other forms of energy. When it passes through a heating element, such as in an electric stove, it is converted into heat. When it flows through the filament of an incandescent light bulb or excites gases in a fluorescent lamp, it is converted into light. When it powers an electric motor, it is converted into mechanical energy that can be used to drive machines. In a nuclear power plant, after electricity is generated, it must be transmitted over long distances to reach consumers. This is done through a system known as the electrical grid. The electrical grid consists of high voltage transmission lines, substations, transformers, and distribution networks. High voltage transmission lines carry electricity efficiently over long distances with minimal energy loss. Before electricity reaches homes and businesses, transformers reduce the voltage to a safer level for use in appliances and electronic devices. Electricity is a fundamental part of modern life, powering almost every aspect of technology and infrastructure. Despite its importance, electricity itself is invisible. It can only be observed through its effects, such as the illumination of a light bulb, the movement of an electric motor, or the heating of a coil. Because electricity involves the movement of subatomic particles, it follows the principles of physics and requires precise control to be used safely and efficiently. Electricity is neither created nor destroyed, but is converted from one form of energy into another. In a nuclear power plant, the energy originally stored in the atomic nuclei of uranium fuel is converted into heat energy through fission. This heat is then used to produce steam, which is converted into mechanical energy in a turbine. The mechanical energy is then converted into electrical energy by a generator. Once electricity is generated, it follows established physical laws as it moves through power lines and circuits to reach consumers. The study of electricity involves multiple scientific disciplines, including physics, chemistry, and engineering. The movement of electrons in conductors follows the laws of electromagnetism described by physicists such as James Clerk Maxwell. The reactions inside batteries and nuclear fuel involve chemical processes that release energy. The design of power plants, generators, and transmission networks involves engineering principles to ensure safety and efficiency. While electricity is an essential part of modern civilization, it requires careful management due to its potential hazards. Electrical currents can cause fires, equipment damage, or injury if not handled properly. Circuit breakers, fuses, and surge protectors are devices designed to prevent excessive currents that could lead to dangerous conditions. Electrical safety regulations govern the design, installation, and operation of electrical systems to minimize risks to people and property. Electricity is also a crucial factor in the transition to sustainable energy. While nuclear power provides a low-carbon source of electricity, other renewable sources such as solar, wind, and hydroelectric power are also used to generate electricity without producing greenhouse gas emissions. The integration of different energy sources into the electrical grid is an ongoing challenge that requires advanced technology and careful planning. Electricity is the flow of electrons through a conductor driven by a voltage difference and controlled through circuits and devices. It is generated in nuclear power plants through a series of energy conversions, starting with nuclear fission and ending with electromagnetic induction in a generator. Electricity can be transmitted over long distances, converted into different forms of energy, and controlled to perform useful work. It is an essential but invisible force that powers modern life, requiring scientific understanding and engineering expertise to be harnessed effectively and safely. Now let's go on to look at what a nuclear power plant is. A nuclear power plant is a facility designed to generate electricity using nuclear energy. It harnesses the energy released from the splitting of atomic nuclei, a process known as nuclear fission. The energy produced in nuclear fission is in the form of heat. Footnote: let's ask ourselves, why in the form of heat? Nuclear fission in a nuclear power plant results in energy release primarily in the form of heat, and this happens due to fundamental physical principles governing the interactions between atomic nuclei, the conversion of mass into energy, and the behavior of the particles released during the process. Nuclear fission occurs when a heavy atomic nucleus, typically uranium-235 or plutonium-239, absorbs a neutron and becomes unstable. This instability causes the nucleus to split into two or more smaller nuclei known as fission fragments. This process also releases additional neutrons and a significant amount of energy, most of which manifests as heat. The energy release in nuclear fission comes from the conversion of nuclear binding energy into kinetic energy. The nucleus of an atom is held together by the strong nuclear force, which acts to bind protons and neutrons together. However, when a heavy nucleus like uranium-235 undergoes fission, the sum of the masses of the resulting fission fragments and the emitted neutrons is less than the mass of the original nucleus. This missing mass is converted into energy according to Einstein's famous equation E equals mc squared, where E is energy, m is lost mass, and c is the speed of light. Even a small amount of lost mass results in an enormous energy release because c squared is a very large number. Most of this energy appears as the kinetic energy of the fission fragments. When the original heavy nucleus splits, the two main fission fragments are ejected in opposite directions at extremely high speeds. Since they have electric charge, They interact with surrounding atoms, colliding with other particles and transferring their kinetic energy to them. This process of collisions results in a dramatic increase in the random motion of atoms in the reactor fuel, which we perceive as heat. A smaller portion of the released energy appears as gamma radiation, a type of high-energy electromagnetic wave. Gamma rays can travel through the reactor and deposit their energy in materials they encounter, further heating the surrounding environment. However, gamma radiation is not the primary contributor to the overall heat energy compared to the kinetic energy of the fission fragments. Additional heat is generated by the neutrons released during fission. These high-energy neutrons collide with surrounding atoms in the reactor's fuel, moderator, and coolant, transferring energy in the form of heat. Some of these neutrons go on to trigger further fission reactions, sustaining the chain reaction that allows a nuclear power plant to operate continuously. Heat production in a nuclear power plant is crucial because it serves as the working energy that drives the entire system. Unlike chemical reactions in a coal or gas power plant where fuel is burned to generate heat through oxidation, nuclear fission releases heat through a fundamental rearrangement of nuclear forces and mass energy conversion. The heat generated in the reactor core must be transferred away efficiently to prevent excessive temperatures that could damage the reactor components. This is achieved using a coolant, typically water, which absorbs the heat from the reactor core and carries it to a heat exchanger or directly to a steam generator. The heated water or steam then drives the turbine, converting thermal energy into mechanical energy, which is subsequently converted into electrical energy by a generator. Even after the fission reactions slow down, heat continues to be generated due to radioactive decay of the fission fragments. These fragments are unstable and continue to emit beta radiation and gamma rays, further heating the reactor core for a period of time. This phenomenon, known as decay heat, is why nuclear reactors require cooling even after shutdown to prevent overheating and potential damage. Footnote: decay heat is the heat that continues to be generated in a nuclear reactor even after the fission chain reaction has been stopped. It arises due to the radioactive decay of unstable fission products that were created during nuclear fission. Even though the main source of heat during the reactor operation is the kinetic energy of fission fragments, once the chain reaction stops, the residual heat comes from the ongoing disintegration of these fragments, which continue to release energy in the form of radiation. During nuclear fission, when a heavy nucleus like uranium-235 or plutonium-239 splits, it forms smaller atomic nuclei called fission products. These fission products are often neutron-rich, meaning they have more neutrons than stable isotopes of similar elements. Because of this excess of neutrons, they are radioactive and undergo beta decay, a process in which a neutron inside the nucleus transforms into a proton while emitting an electron, which is the beta particle, and an antineutrino also is emitted. Each time a beta particle is emitted, it carries away some energy, but much of the energy remains in the recoiling nucleus, which then collides with surrounding atoms. This collision transfers energy to the surrounding material, causing an increase in temperature, which we experience as heat. This is why decay heat exists. The radioactive fission products still contain energy that they gradually release as they decay into more stable forms. In addition to beta decay, some fission products also emit gamma rays, which are high-energy electromagnetic waves. These gamma rays travel through the reactor core and deposit their energy as they interact with surrounding materials, further heating the system. Unlike beta particles, which interact quickly with surrounding atoms due to their charge, gamma rays can travel longer distances before being absorbed, spreading heat throughout the reactor structure. Another contributor to decay heat is alpha decay, though this is less significant in the short term. Some heavy fission products and transuranic elements such as neptunium or americium, which form neutron absorption in uranium fuel, undergo alpha decay, emitting helium nuclei, which are alpha particles. These particles also deposit energy in the surrounding material as they slow down, but their contribution to decay heat is smaller than that of beta decay. The total amount of decay heat present after a reactor is shut down depends on how long the reactor was running and at what power level. If a reactor has been operating at high power for a long time, a large number of fission products have accumulated, and many of them are still highly radioactive. This means that when the reactor is turned off, the decay heat will initially be quite high and will only decrease gradually over time. Immediately after a reactor shuts down, decay heat is typically about 5% to 10% of the power level the reactor was producing before shutdown. This means that if a reactor was generating 3,000 megawatts of thermal power, the decay heat would still be around 150 to 210 megawatts right after shutdown. This is enough heat to cause serious damage if not properly managed. Over time, as the radioactive isotopes decay, the amount of decay heat decreases. Within 1 hour, decay heat typically drops about 1% of the original reactor power. Within a day, it falls to roughly 0.4%, and after a week, it is around 0.2%. However, even though these numbers seem small, they still represent significant amounts of heat. In large reactors, even 0.2% of full power can mean several megawatts of heat, which is more than enough to cause fuel damage if cooling systems fail. Decay heat is the primary reason why nuclear reactors require cooling systems even after shutdown. If cooling is lost, the residual heat can cause the temperature in the reactor core to rise uncontrollably. If this happens, the fuel rods, which contain uranium or plutonium in ceramic form, can become so hot that they start to melt, leading to a core meltdown.
This is what happened in nuclear accidents like 3 Mile Island, 1979, and Fukushima, 2011, where loss of cooling caused fuel overheating and severe reactor damage. To manage decay heat, nuclear power plants use residual heat removal systems or emergency core cooling systems (ECCS). These systems ensure that coolant continues to flow through the reactor core even after shutdown, carrying away excess heat. Many modern reactors also have passive cooling systems which rely on natural convection and gravity to circulate coolant without requiring external power. Even spent nuclear fuel, after being removed from this reactor, continues to generate decay heat. This is why used fuel rods are first placed in spent fuel pools, which are large pools of waters designed to provide cooling and radiation shielding. The water in these pools absorbs the remaining heat and allows the fuel to cool down gradually. After several years, when decay heat has dropped significantly, the fuel can be transferred to dry cask storage, where it is kept in air-cooled containers designed for long-term storage. The physics behind decay heat also plays a role in nuclear waste management. Some fission products decay quickly and stop generating heat within hours or days, but others have much longer half-lives, meaning they continue to produce small amounts of heat for decades or even centuries. This long-term decay heat is one of the reasons why high-level nuclear waste must be stored in secure facilities for extended periods. In summary, decay heat occurs because the fission products left behind after nuclear fission are still radioactive and continue to release energy as they decay. This heat primarily comes from beta decay, along with contributions from gamma radiation and alpha decay. Even though the reactor has stopped fissioning, decay heat persists and must be managed to prevent overheating. This makes post-shutdown cooling systems essential in all nuclear power plants to avoid accidents. Footnote closed. Going to the original sentence that we were reading. A nuclear power plant harnesses the energy released from the splitting of atomic nuclei, a process known as nuclear fission. The energy produced in nuclear fission is in the form of heat. This heat is used to convert water into steam, which then drives turbines connected to generators. Okay, let's ask ourselves. It says the heat is then used to convert water into steam. But how? How is it used to convert water into steam? In this nuclear power plant context, heat conversion in a nuclear power plant follows a precise sequence of steps that ensure maximum energy transfer from nuclear fission to steam generation. The process takes place within a controlled system where heat is transferred from the reactor core to water, turning it into steam that powers turbines. The primary source of heat in a nuclear reactor is nuclear fission, where the splitting of heavy atomic nuclei such as uranium-235 or plutonium-239 releases a large amount of energy. This energy is primarily in the form of kinetic energy carried by the fission fragments, which are smaller atomic nuclei produced after fission. These fragments move at extremely high speeds and collide with surrounding fuel atoms, transferring their kinetic energy and causing the temperature within the reactor core to rise significantly. The fuel rods inside the reactor core contain the fissile material in the form of small cylindrical pellets of uranium dioxide, UO2, or another nuclear fuel. These pellets are stacked inside long, sealed metal tubes made of zirconium alloy, which is chosen because it has a high resistance to heat and does not easily absorb neutrons. The fuel rods are arranged in bundles called fuel assemblies, which are submerged in a coolant to facilitate heat transfer. The coolant is a liquid or gas that absorbs heat from the reactor core and carries it away to be used in steam generation. In most nuclear reactors, water serves as the coolant, while in some advanced reactors, liquid sodium or helium is used. The choice of coolant depends on the reactor type, with pressurized water reactors (PWRs) and boiling water reactors (BWRs) being the most common. In a PWR, pressurized water reactors, the coolant is kept under high pressure to prevent it from boiling while it flows through the reactor core. The pressurized water absorbs heat from the fuel rods and then travels through pipes to separate component called the steam generator. And then travels through pipes to a separate component called the steam generator. The steam generator is a heat exchanger where hot pressurized coolant transfers its heat to a secondary loop of water, causing it to turn into steam. The coolant itself remains liquid and is recirculated back into the reactor to absorb more heat in a continuous cycle. In a BWR, boiling water reactors, the coolant is allowed to boil directly within the reactor vessel. As the water absorbs heat from the fuel rods, it turns into steam within the reactor itself. The steam is then directed through pipes to the turbines, eliminating the need for a separate steam generator. Because the steam in a BWR comes directly from the reactor, it carries trace amounts of radioactive particles, requiring additional containment measures. In both PWRs and BWRs, once the water has absorbed enough heat, it undergoes a phase transition from liquid into steam. This transformation occurs when the water reaches its boiling point, which depends on the pressure conditions within the system. Under normal atmospheric pressure, water boils at 100 degrees Celsius, 212 Fahrenheit. But inside a pressurized reactor system, the boiling point can be much higher. In a PWR, where water is kept about 155 bar, which is 2250 psi, 2250 psi, the temperature can exceed 300 degrees Celsius, 572 Fahrenheit, without boiling. Can exceed this without boiling. In a BWR, where the pressure is lower, water boils at approximately 285 degrees Celsius, 545 Fahrenheit. The steam that forms is a high-energy gas with significant pressure and temperature. it is directed through a system of pipes toward the turbines, where its thermal energy is converted into mechanical energy. Before reaching the turbines, the steam may pass through moisture separators and reheaters to remove excess water droplets and maintain efficiency. Wet steam, which contains liquid water, can cause damage to turbine blades. So it is essential to ensure that only dry steam reaches the turbine. Once the steam has done its work by spinning the turbine blades, it must be condensed back into water so it can be reused in the cycle. This is accomplished in the condenser, a large heat exchanger that cools the steam by passing it over a network of pipes containing cold water. The cooling water comes from a natural source such as a river, lake, or ocean, or it may be circulated through cooling towers that release excess heat into the atmosphere. The condensed water is then pumped back into the reactor or steam generator to repeat the process. Throughout this entire system, precise control is maintained to ensure that heat is transferred efficiently while preventing overheating or pressure imbalances. The flow rate of the coolant, the pressure in the reactor vessel, and the temperature of the steam are continuously monitored and adjusted by automated control systems and human operators. Safety mechanisms such as emergency cooling systems and pressure relief valves are in place to respond to any anomalies. This entire process from nuclear fission to steam production operates in a continuous loop, providing a steady supply of steam to drive turbines and generate electricity. The efficiency of steam production is critical to the overall performance of a nuclear power plant, as any disruptions or inefficiencies in heat transfer can reduce power output or pose safety risks. Having the question answered and returning to the original statement, the energy produced in nuclear fission is in the form of heat. This heat is used to convert water into steam, which then drives turbines connected to generators. The generators convert mechanical energy into electrical energy, which is then supplied to the power grid. A nuclear power plant contains one or more nuclear reactors. A nuclear reactor is a controlled environment where nuclear fission occurs in a sustained and regulated manner. The fission process is initiated when a neutron collides with a heavy atomic nucleus such as uranium-235 or plutonium-239. When the nucleus splits, it releases energy in the form of heat and additional neutrons. These released neutrons can trigger further fission reactions, creating a self-sustaining chain reaction. To control the rate of fission, nuclear reactors use control rods. What are control rods? They are a critical component of a nuclear reactor, designed to regulate the fission chain reaction and ensure that the reactor operates safely and efficiently. They are long, slender rods made of materials that absorb neutrons, which are the subatomic particles responsible for sustaining the nuclear chain reaction. By controlling the number of free neutrons in the reactor core, control rods allow operators to adjust the power output, shut down the reactor, or maintain a stable reaction rate.
In a nuclear reactor, the process of nuclear fission occurs. Well, the splitting involved in the nuclear fission reaction releases a large amount of energy in the form of heat and also produces additional neutrons. These newly released neutrons can strike other fissile atoms, causing them to split and release more neutrons, creating a self-sustaining chain reaction. Without control, this reaction could escalate uncontrollably, leading to excessive heat generation, potential fuel damage, and, in extreme cases, a meltdown. Control rods prevent this by absorbing some of the free neutrons, thereby regulating the reaction. The materials used in control rods must have high neutron absorption capacity while remaining structurally stable under extreme temperatures and radiation exposure. Common control rod materials include boron, cadmium, hafnium, and silver indium cadmium alloys. Boron is particularly effective because its atomic structure allows it to capture neutrons efficiently, forming stable isotopes that do not contribute to further fission reactions. Cadmium also has a high neutron absorption cross-section, meaning it is highly effective at capturing neutrons before they interact with fissile material. Hafnium is often used in reactors that require long-lasting control rods, as it is highly resistant to corrosion and radiation damage. Control rods are inserted into the reactor core alongside the fuel rods, which contain the fissile material. The fuel rods contain the fissile material. Alongside those fuel rods are kept in the control rods. Their positioning, the control rods' positioning with the core determines how many neutrons are absorbed and consequently how much fission occurs. Inserting the control rods deeper into the core increases neutron absorption, slowing or stopping the chain reaction. Withdrawing them reduces neutron absorption, allowing the reaction rate to increase. The movement of control rods is carefully controlled by automated systems and reactor operators to maintain safe and stable operation. Control rods play a key role in starting up, shutting down, and adjusting the power level of a nuclear reactor. During startup, the rods are gradually withdrawn from the core to allow fission to begin. The rate of withdrawal is carefully controlled to prevent sudden power surges. Once the reactor reaches the desired power level, the rods are positioned to maintain a steady reaction rate. During normal operation, small adjustments to the rod positions can be made to compensate for changes in fuel composition and reactor conditions. In the event of an emergency, control rods provide a rapid shutdown mechanism known as a SCRAM. A SCRAM is an emergency procedure in which the control rods are fully inserted into the core within seconds to immediately halt the chain reaction. This is typically done by gravity, springs, or hydraulic pressure to ensure rapid response even if electrical power is lost. A scram is triggered automatically if sensors detect dangerous conditions such as excessive temperature, pressure fluctuations, or a reactor coolant system failure. The design and arrangement of control rods vary depending on the type of reactor. In pressurized water reactors, PWRs, control rods are inserted from the top of the reactor vessel and move vertically. They are suspended by mechanisms that allow precise adjustments to their position. In boiling water reactors, BWRs, control rods are inserted from below the reactor core, pushed upward by hydraulic pressure. This design is necessary because the boiling water inside the reactor vessel makes top insertion impractical. In some advanced reactor designs, control rods work alongside other neutron-absorbing mechanisms. Some reactors use burnable poisons, which are materials incorporated into the fuel that gradually absorb neutrons over time, reducing the need for frequent control rod adjustments. Others use liquid neutron absorbers, such as boron solutions, which can be injected into the coolant to supplement control rod functions. Over time, control rods experience wear and degradation due to constant neutron bombardment and high temperature conditions. The materials can undergo swelling, embrittlement, or changes in absorption properties. To maintain safety and efficiency, control rods are periodically inspected, replaced, or adjusted. In some cases, older rods are removed and replaced with fresh ones, while in others, their positions are modified to optimize performance. Control rods are indispensable to the safe and controlled operation of a nuclear reactor. They provide the primary means of regulating fission, ensuring that the reaction remains stable and does not accelerate uncontrollably. They enable precise power adjustments, facilitate reactor startup and shutdown, and serve as a crucial safety mechanism in emergencies. That was the answer to the question, what are control rods? Continuing the original sentence and repeating the first one. To control the rate of fission, nuclear reactors use control rods. Control rods are made of materials like boron or cadmium, which absorb neutrons and prevent excessive reactions. By inserting or withdrawing control rods, operators can regulate the reactor's power output. If too many neutrons are absorbed, the reaction slows down or stops. If fewer neutrons are absorbed, the reaction speeds up. A nuclear reactor contains fuel rods that hold the nuclear fuel. Well, expanding on that too, fuel rods are the core components of a nuclear reactor, containing the fissile material that sustains the nuclear chain reaction and produces the heat necessary for power generation. They are long cylindrical tubes filled with nuclear fuel, arranged in bundles to form the reactor core. Their design and composition are crucial for ensuring the efficient and controlled release of energy while maintaining safety and structural integrity under extreme conditions. The primary purpose of fuel rods is to house and manage the nuclear fuel. which consists of fissile isotopes capable of undergoing fission. The most commonly used fuel is uranium-235, U-235, in the form of uranium dioxide, UO2, a dense ceramic material with high melting stability. In some reactors, plutonium-239, Pu-239, or mixed oxide, MOX fuel, which combines uranium and plutonium, that is mixed oxide, is used as an alternative. The fuel is processed into small cylindrical pellets, each about the size of a fingertip, which are stacked end to end inside the fuel rods. The fuel rods themselves are made from a strong, heat-resistant metal alloy that can withstand extreme temperatures and radiation levels inside the reactor. The most common material used is zirconium alloy, often referred to as zircalloy. Zirconium is chosen because it has a low neutron absorption rate, meaning it does not interfere significantly with the fission process, while also being highly resistant to corrosion and mechanical stress. The tubes are sealed at both ends to provide the release of radioactive material and to maintain structural integrity during reactor operation. When a reactor is operating, neutrons released from fission interact with the fuel inside the fuel rods, causing more uranium-235 atoms to split. This chain reaction releases enormous amounts of energy, mostly in the form of heat, which is absorbed by the surrounding coolant. As the reaction continues, the fuel gradually depletes, and the concentration of fissile material decreases. Over time, fission products, fragments of split atoms, accumulate within the fuel pellets, some of which are gases such as xenon and krypton. These gases create internal pressure within the fuel rods, which is carefully accounted for in their design. To manage this buildup of fission gases, fuel rods are designed with a small space inside to allow gas expansion. Additionally, many fuel rods contain a small reservoir called a plenum, where these gases can collect without compromising the structural integrity of the rod. Special materials such as neutron-absorbing elements or burnable poisons like gadolinium may also be incorporated into the fuel or fuel rods to help regulate reactivity over time and ensure steady power output. Fuel rods are assembled into fuel assemblies, which are structured arrangements of multiple rods held together by a metal framework. In a pressurized water reactor (PWR), a typical fuel assembly contains about 200 to 300 fuel rods, whereas in boiling water reactor (BWR), an assembly might have fuel rods but a different structural design. The number of assemblies and their arrangement within the reactor core determine the overall power output and efficiency of the reactor. The lifespan of a fuel rod depends on factors such as reactor type, power level, and fuel enrichment. Typically, fuel rods remain in the reactor for several years before they are removed and replaced with fresh fuel.
As they burn up, their efficiency decreases, and they accumulate radioactive fission products that absorb nutrients, gradually slowing the chain reaction. To maintain this, nuclear plants follow a fuel cycle strategy in which some fuel rods are periodically removed and replaced, while others remain in operation to maintain balanced reactivity across the core. Once removed from the reactor, spent fuel rods remain highly radioactive and generate residual heat due to the ongoing decay of fission products. They must be carefully stored and cooled in a spent fuel pool. A large water-filled basin. Let me repeat that again. They must be carefully stored and cooled in a spent fuel pool, a large water-filled basin that provides both shielding from radiation and passive cooling. Over time, as their radioactivity decreases, they may be transferred into dry cask storage, where they are encased in thick radiation shielding containers for long-term management. Some countries pursue reprocessing where usable fissile material is extracted from spent fuel rods and recycled into new fuel. Fuel rods must withstand extreme conditions, including high temperatures, intense radiation, and mechanical stress caused by thermal expansion and coolant flow. Any structural failure, such as a breach in the cladding, could release radioactive materials into the reactor coolant, potentially leading to safety concerns. To prevent this, rigorous quality control, regular inspections, and advanced materials research are integral to fuel rod design and maintenance. Fuel rods are the heart of the nuclear energy production, serving as the primary medium for controlled nuclear fission. Their design is a balance of efficiency, durability, and safety, ensuring a steady and predictable power output while preventing the release of harmful radiation. Without fuel rods, a nuclear reactor would have no means of sustaining a controlled chain reaction, making them one of the most essential components in the entire nuclear power generation process. Returning to the original statement, a nuclear reactor contains fuel rods that hold the nuclear fuel. Fuel rods are long cylindrical tubes filled with pellets of uranium and other fissile materials. These rods are arranged in bundles called fuel assemblies. The fuel rods are placed inside the reactor core, which is the central part of the reactor where fission takes place. The reactor core is surrounded by a moderator, a substance that slows down neutrons to increase the likelihood of fission. Common moderators include water, graphite, and heavy water. The reactor generates immense heat, which must be removed to prevent overheating. This is done using a coolant. The coolant is a fluid that transfers heat from the reactor core to another part of the planet where the heat can be used. In most nuclear power plants,